Okay, everyone, let's take a look at this scenario. Let's say Julio has $10 in his bank account. He gets a job and starts to save $10 a week from his paycheck. So he starts off with $10 in his bank account. That's his initial amount of money, right? After 1 week of saving from his job, he has $20, right? After 2 weeks, he has $30, right? After 3 weeks, he has $40, and after 4 weeks, he has $50, right? So clearly, the outputs of this function, the amount of money he has at the end of each week, is an arithmetic series, right? Because it increases by the same amount each time. So I'm going to introduce a new term for these kind of relationships. These kind of relationships we're going to call linear. We're going to call them linear. And particularly, if we think of this as a function, we're going to call these linear functions, okay? Linear functions. Why would we call them linear? Because let's see here, we can draw a straight line through them, right? And we can think of this relationship as being modeled by a straight line, okay? So let's remember something about lines. Well, if a line is straight, right, that means the output is going to change by the same amount each time, right? That means it's going to have a common difference. So let's remember our old equation for lines. Hopefully we all at least remember having seen this before. Y equals mx plus b. And of course the mx means m times x, right? So y, we remember to be the y value of the line, or the y coordinate, right, at any point on the line. X, right, is the corresponding x coordinate at any point on the line. Do we remember what m was? M, right, was slope. M was slope, right? But now that we're considering these linear relationships as lines, the slope is the same thing as the common difference, right? It's the same thing as the common difference, right? Because if Julio is saving $10 a week, that means the amount of money he has is changing by the exact same number each time, right? In this case, it's changing by 10 to represent the $10 he's saving. So his common difference is 10. And when we model relationships like this with a line, the slope is the common difference, okay? We can also consider that the rate of change, right? Because the common difference is the rate at which any linear relationship is changing, right? And do we remember what b means? Let's try to remember what b means. B means, I hope we remember, is the y-intercept, right? Intercept. B was the y-intercept, right? Well, what's the y-intercept? The y-intercept is the spot at which the line crosses the y-axis, right? We could also consider that the initial value, right? Initial value. We can also consider that the initial value because that's the point where x equals 0, right? That's the point where x equals 0. So I also want to introduce a function notation to this, right? Do we remember that the outputs of a function are graphed on the y-intercept, right? So if we're going to consider this linear relationship as a linear function, which it is, we can just write it as f of x equals mx plus b, right? These two things are saying the exact same thing, right? Because where do we graph the values of the output of a function? We graph them on the y-axis. So y is equal to f of x, right? Just different ways of essentially saying the same thing, right? Now we do have different ways to refer to these two different forms of writing. They're just very slightly different, right? When we write it as f of x equals mx plus b, we call that the explicit form. We call that the explicit form because we're outright telling you that this is a function, right? We're actually using function notation to make it super clear that this is a function. When we write it as y equals mx plus b, we call that implicit form. Implicit form. Because written this way, it still is a function, but we're not outright telling you it's a function by actually using the function notation, right? So the fact that this is a function, we can think about it as being implied, right? So we call this implicit form. Just remember that when we write a linear function as f of x equals mx plus b, we just call that explicit form. When we write it as y equals mx plus b, we call that implicit form. Okay, everyone, I just want to go through the meaning of all this notation again, okay? So remember, we're dealing with linear functions. Those are functions whose output changes by the same amount, or rather, I should say, whose output changes by a constant amount. They are functions that can be represented by a straight line. That means if you plot a bunch of points of the function on the coordinate plane, you can connect them all with a straight line. So that means the function relationship can be modeled by a straight line. Okay. Remember the familiar equation for a line is y equals mx plus b. We're going to call that the implicit form if we're talking about linear functions. And the explicit form is just writing f of x equals mx plus b, explicitly letting everyone know that this is a function. Let's remember that in this case, y, or f of x, that's the value of the function, right? That's the output of the function. M is the slope of the line representing the function. It's also the common difference of the output, right? And it's also the rate of change. X is the input of the function, right? And B is the y-intercept of the line that represents the function. That's the point where the line intersects the y-axis. It's also the initial value of a function relationship, of a linear relationship. And it's also the value of f of 0, right? Because if we plug in, let's make a little bit of room here, right? If we plug in f of 0 to mx plus b, that's going to give us m times 0 plus b, right? What's m times 0? Well, anything times 0 is 0, so that's going to cancel out, and we're going to have f of 0 equals b, which should make sense if b represents your initial value.